I can mark it with this, and I can drag this out. That's about 78 watts, and then I have this peak here. So let's see what is that peak power. So we go ahead and see if this will work. Do it manually. Sometimes this detects the peak, but sometimes it doesn't. All right, so I'm going to mark this point here, the motor sheet, and what we're going to do is zoom in. Line-to-line voltage here. So I'm going to pick up this probe, open it up here, and here. And that gives us line-to-line voltage. Let me just get rid of the other ones. Does that make sense to you? Zoom in, let's see. You want to add it? What do you want to do? You want to
add 2 more blocks.
okay. Okay, so you want to add VB and VC
Here.
separate.
Yeah, separate.
Shows up. What do you think? Okay. Pardon me?
This is not correct. That overlapping also is not understood.
This overlapping.
Just down below one.
This one.
And then those 2 voltages also are not correct.
Okay, let's see here. This
Just one portion.
This is the zoom portion. So the bottom we have is VA minus VB. So it's basically this minus this minus this.
Just zoom it further and we'll take 1 minute.
Zoom in here. let's say when you're trying to develop a blower, fan blower, which is going to sell in the market for, well, if I say US, let's say I want a blower for $20, right? It's made in China, so you have a single side PCB, you have got all these components. Now, of course, microcontroller is one aspect of it. Other part is using, for example, Motorola IC, very old IC, I think it's called MC3030 or something of that sort, which is meant for those kind of applications. That IC is still being used. It's, I think, 20, 25 years old IC, which is still being used today. So, and the cost pressures are high when you're trying to, even when you're trying to do a high-speed, let's say, washing machine, a very low-cost, high-speed washing machine used in China. I think the one employed in the US are different, but so the cost pressures force you when you are actually trying to shave off 1 cent, 2 cents here and there, then it becomes a very critical choice that which one you use, because the other part is that when I use a high-side PWM, I don't have to use drivers, and each driver costs $1. For example, I mean, IR driver, you use IR 2103 or something, they cost $1. Now $1, I think, is a lot of money. Pardon me?
Yeah, in the $20 anyhow, $1 is a big.
That's right. So you're trying to optimize your cost, right? So that's where you wrestle with what choice is going to give you the best bang for the buck, and that's where you end up actually going through the different PWM schemes and verifying which is going to work best for you. Okay. All right. So nothing else on this one. I think that was a great contribution here. So let's go back to.
So we'll be able to run this example on the CD?
Yes. Yes, they are working examples.
And are they, the number of nodes is smaller than what PSpice, the student version gives? Or?
I think it's very close. If it is not, we're happy to convert them. They should be able to run in the. We try to simplify it as much as possible, but we haven't verified it with the student version. But I think it's easy for us to. The only thing you will not be able to run is amplifier. You will have to replace it with a Laplace block. All right, so we have. Now here is. Let's do some phase advance and phase lag example. This will show us parametric analysis. Okay, we have the same circuit as before, and we have the same logic as before, high side, and same integrator as before, same PWM generation scheme. Parameter files is exactly the same, except that here we begin to play with the delay 1. So you can see that we set delay 1 to 0. Okay, this is where you begin to play with, and okay. So when delay 1 is equal to 0, that means your current is going to run into this ramp of the voltage. Earlier, we were basically making such that the current started when the voltage was steady. So what happens when you begin to run into the ramp of the voltage? Now this is happens quite often because your Hall sensor signals are not aligned in your motor. So you have a phase shift or phase lag. So let's look at what happens to your performance when you begin to have a shift in your current. We have, and then we simulated up to a delay of 750 microseconds, which is slightly more than 30 degrees. I think 30 degrees comes to about 680 microseconds. So slightly more. So there's a phase advance and there's a phase lag of the current. This essentially is your so this is basically your back EMF voltage A phase and current A phase. This is a waveform when you're lagging a little bit. Okay, this waveform looks pretty well behaved. You have a basically delay 1 of 750 microseconds. So when you have a delay, your waveform looks pretty well behaved. Not too bad so far. And when you have, so this is the parametric analysis we did from delay 1 of 0 to delay 1 of 750 microseconds. And you can see this ring, this quadratic effect coming into place where your current begins to ring. Right? Now this is where you can have serious issues, torque ripple issues, and you can have power dissipation issues, very poor performance of the drive. So when you have this kind of issue, which can be quite common in your if your all sensors are not perfectly aligned. Even for a $20 fan blower, you can't afford to have this kind of performance. This is the input current. This is for we'll come back to this. Now we have plotted. We did the FFT and we plotted the efficiency. So we had about 85.6% efficiency for the given motor when delay was 750 microseconds. We have got output power of 41.16 watt and input power of 48.05 watts. This is the FFT at 750 microseconds. Now the other interesting part you have here is this 40 watt spike at 20 kilohertz. Now, and then you have got 12 watt here. Now, what is the significance of this 20 kilohertz spike? What is, so you have a DC power 48 watt, and this is input power. Input power we are talking about. Now, input power, you have high frequency harmonics. What does that mean? So you have a multiple of switching frequency. This one is 20, 40, 60, 80. You have nothing at 100, so the fifth harmonic is missing. Then we have 6, 7, 8, 9, and I think the 10 may be missing. So one implication it has is on your input capacitor selection. Especially when you have a battery-powered source, right? But especially when you're running, it's significant in electric vehicles. This is where when you do frequency, when you do system modeling, you want to introduce battery later on because you have battery. Let's just say that it has got an inductance and a resistance. Okay. So when I'm feeding this directly to the inverter, who is going to supply that 20 kilohertz of power? This will not supply it. So you have to pay careful attention to these harmonics so that you can say, okay, I really want to put a capacitor, and then the impedance of that capacitor has to be such that you can supply 20 kilohertz, and I think you may have to, in this case, supply all the way up to, let's see here, 20, 40, 60, 80 kilohertz of ripple from this capacitor. That's the only source which is going to supply all those harmonics. So the impedance of this capacitor becomes critical. So the electrolytic which you choose, plus you will have to put some film capacitor across it, so that the impedance, you can say, can supply those currents. So you could actually, if you have a battery source, you could model the battery source with approximate inductance and resistance, and then also model your capacitors to see if that particular currents are being supplied. So that's another part you can see is for a particular motor, when you run different PWM schemes, you can look at different input capacitor requirements. Especially, it's even true for other sources, but for battery sources especially, it becomes critical. Electric vehicles, it becomes critical.
So what if the capacitor is not present? The battery is supposed to be present.
Well, what's going to happen actually is that your this voltage here is not like this anymore, right? So you have got voltage which may have, so your performance of the drive becomes, yeah, it becomes quite.
Is 40 watt not very significant at 20 kilohertz?
It is, isn't it? It is significant.
So is it because of the second square wave? Is it because of the lower side square wave? Because as you go, I just assuming as you go to the other PWM techniques, the 40 watt will go down. That's what I'm assuming. If that is the case, it will be the same.
You're saying that
If you go for PWM top and bottom,
right.
so current should be same.
The FFT, no,
FFT, I'm talking about
FFT.
it will be the same.
I don't think that is the case, because
It's not, it is gone down.
see that particular FFT, that it is very dependent on the PWM scheme.
Because line voltage will get cancelled.
That is because of the switching frequency. This 20.
It is because of switching frequency, but also it has an impact on, see, diode plays a major part. Diode in the three-phase, so if you can anytime make sure the diodes don't activate, right, that requirement goes down. So when you do PWM all the time, your filter requirements may be less, because you're able to, you have almost synchronous rectification, right? Because when you are changing the phase, you're not conducting through the diode, you're conducting through the MOSFET switch. So that's where there is a significant impact on what PWM scheme you use on your FFT.
If it doesn't go down, there is no point in really going for a six-phase.
That's right. That's right. That's right.
Is that also there in the slide somewhere?
We have not, I don't think we have done a side-by-side comparison. This was just to illustrate one point. Okay, so, and here is what happens when you go to delay 0. So you lost 4% of your efficiency, plus you have lost power. Right, so that's a significant. So for a that's a significant. And here you can see that actually your filter requirement has gone up as you have moved away from the sweet spot, as you have moved away from the 600 or the 750 microsecond or 680 microsecond delay. So that shoots up. That basically puts a burden. The ringing has significant impact. You know, the quadratic effect has significant effect on your filter requirements. Okay, so we're gonna let's see here. So we're going to fire up demo 2. Close this. This should be quite interesting because we're going to increment in 150 microsecond and go to 750 microseconds. Right? So this is a parametric thing we're going to do, and it'll take a little bit of more time than the last one. So we're going to get this. All right. So we have a problem. So what we're going to do is looking for files. So let me just go back here. We're going to you have a DC power, and then you have a power at frequency 1, 2, and 3. Right, various frequencies. Basically, those are the various components of this power. Now, the DC power essentially is your dissipative power, resistors, effective power, right? That is your effective power. Now, this component here we have currently is 49 watts, right? 49 watts. That's in one case. Now, where is that power going? That's the question. Yeah, right? Where is that power going?
Where is it coming from?
But it's definitely coming from the source.
So then you're